Hello and welcome to yet another session on bio-inspired optimization technique. Today our goal is to explain the Pelican optimization technique, where the technique mimics or the technique is inspired by the food foraging behavior of the pelican birds. The way the pelican birds search, identify and catch their prey, that same process was mimicked in this optimization technique. So let us begin with an example. So our example is the objective equation is y is equal to x square. So let me use some prominent color. The y is equal to x square is our objective equation. As usual, this x is our design variable that you have to change y. This y is the objective variable. Okay, and x has a constraint, not a, but two constraints, upper bound and lower bound, which is, let us say, -100 to 100. So you can take any value of x within -100 to 100, not equal to -100 and 100. Any value within -100 to 100 you can take and put it into this equation and find the value of y. And this is, let us say, this is a maximization problem. More the value of y, more optimal is the solution. Okay, so in case of Pelican optimization technique, our first step is to initialize the population, as is the case for the most of the particle swarm optimization techniques. I will not say particle, sorry, I will say swarm optimization technique. Okay, so in case of this initialization, you have to select randomly how many number of agents, or rather to be more relatable with the pelican bird, how many number of pelicans you will consider in their group or swarm of birds employed for searching and finding food. Okay, so for this example I will take only 3 birds for simplicity, and I will generate randomly from the feasible domain 3 new values of x. So to generate that 3 new values, this is the formula I will use. This is the most common formula used for initializing a population when we are dealing with a metaheuristic optimization technique. This formula is nothing but lower bound plus random multiplied by upper bound minus lower bound. This random function is actually nothing but the function randomly select a value, a fractional value, which comes in between 0 to 1. Okay, so any value in between 0 to 1 but not equal to 0 and 1, remember that. So those values are selected and the pattern or distribution function followed is normal distribution. This is the most common and basic distribution function. In the world, most of the data set followed a normal distribution pattern, or assumed to be follow a normal distribution pattern. And this is upper bound of the constant and lower bound of the constant. In our case, lower bound is -100, upper bound is 100. Put into this value, you will find a x. Do it 3 times. So you have 3 agent, that means 3 new values. Many say it as position also. Okay, so these are the 3 new values of the 3 birds generated by this simple formula. Now you do one thing. As we have got x1, x2, x3, put it into this objective equation and find y2, y1, y2, y3, the objective function. And now we have to check whether y1 is greater than y2 or y2 is greater than y3, right? This is actually the fitness function. In case of optimization technique, always remember the value of objective function at a iteration is the fitness function. Most of the time it is so. So here you see the next step. In the next step, which is very commonly known as exploration, where we explore the search domain, the region of feasibility or region of eligible values of search domain. The region of feasibility is earmarked by this minus and 100. Clear? So this is our region of feasibility or region of eligibility, whatever way you may call it or refer it. And you can take any values within this and put it into X to find the value of Y. Our goal is to maximize Y. So more the value of Y, more optimal it is. Or more, that means not more, you are going towards optimality. Okay. So we have done that. Now we have generated x1, x2, x3 with the help of this formula, found the value of y1, y2, y3, compare with them. The maximum is your best bet or best solution always, because we are in the maximization problem. Now before this exploration step will begin or phase will begin, we have to identify which one among these three birds is your target, or the bird which has already identified the prey and it is going towards it. Generally what happens, once one of the population identifies a prey or food, it starts moving towards that, and the other member of the population follows that member. So for that time, that member which has already identified the prey is the leader. Okay, all other birds will follow their leader. Clear? So we have to identify that target. In this case we refer that leader as target or sometimes as prey. That means not prey, but a bird that has already identified the prey, identified the location of the prey. Okay, so in this case let us say y1 is the prey. You can select randomly. Okay, and y1 is the prey. Now any value which is greater than this y1, which is the prey, if that is the case, then for that agent or that bird you have to use this formula to generate a new position or new value of x. Okay, let it be more precise. We have identified this as the prey or target. Now y2, you found that is y2 is greater than y1. Okay, so you will use for generating value of x2, you will use this formula, this one. If it is not so, if y2 is not greater than y1, please note down carefully, if y2 is not greater than y1, then you have to follow this formula. Else, what is else? This. The formula is self-explanatory. If y2 is greater than y1, which is the prey, that is why they are said fitness function of prey. They are not saying fitness function of all the iteration, best fitness function of all the iteration, or like that. They are saying fitness function of the bird or agent that you have identified as the bird or agent who have already identified the prey. That fitness function must be outclassed by your present fitness function. If that is the case, then you will use this formula, the first one. If not, that is not the case, then you use the second one. It is as simple as that. And this xij is the old value of x for that specific agent for which you are comparing. That means if it is the second agent, then this is the old value of x, this one, x2. Okay, in the similar manner for y3 you will put the old value of x3 here. So this x is old value, this x is old value, this is the value of x of the target or prey, that means this one y1, right? So that is why this p means prey. Okay, so this is the value of x for prey, that means this one. This is the old value of your second agent for which you are comparing, and this is also the old value of your second agent. Random function I have already discussed, this and this are same. So by this just compare whether your fitness function or the value of y for your prey is less than the value of y for the second agent. If that is the case, then 1. If that is not the case, 2. This is the simple thing you have to do. I think it is clear. One by one you have to take agent. If you have 3, you have to do this check for 3 times. Yes, also for the prey agent, that is the agent which is already identified as prey. For that also you have to use this check. Okay. So 3 means 3 agents you have considered, 3 times you will check. 5 agents, 5 times you will check, and so on. Now exploration, in the exploration phase, what will happen? You will find either the same 3 values of x, or within 3 one is new value of x, another 2 is same, or another 2 value of x is new, third one is same, and so on, based on this check. Okay, this is the check. I think it is clear. So the check will decide whether a new value of x will come or the old value will remain. So accordingly your y will also be updated. If you find a new x for one of the agent, for that agent the y value will change. But for the other agent who will remain with the old x, I will not say that old value of x will remain. You will use the value of x generated by the second equation. If there is a new value of x, that means you have used the first equation. If there is a old value of x, that means you have used the second equation. Okay, that will be more precise. What I want to say is that if your fitness function, the agent fitness function, cannot outclass the prey fitness function, equation 2 will be used. If they have outclassed, then equation 1 will be used. Clear? That's all. Next is phase 2. This phase is known as exploitation phase. Some say it as global search, some say exploration as local search, exploitation as global search. Okay. Now for that case it is simple. For the 3 agents, 3 new x need to be generated again, and for that you have to, this time you have to use this formula. Okay. So this is the new x, this is the old x, this is the r, which is all times 0.2 multiplied by 1 minus, this is the current iteration, this is the maximum iteration, multiplied by maximum iteration allowed. Say you have allowed 1000 iterations, so cap t will be 100, and you are at 50th iteration, then the small t will be 50. Clear? Multiplied by 2 multiplied by random function, this random function, this random function, this random function, this random function, all are same, and this xij is again the old value of x of the agent for which you are trying to generate a new value of x. These are all old value of x. Okay, for each 3 agent you need to find again 3 new values of x. For that you have to use the old value of x. So for agent 1 you have to use the old value of x for agent 1, this for agent 2, for agent 3 old value of agent 3. Simple. Okay, so new, after this exploitation you have 3 new values of x for the 3 new agents you have. and accordingly again you try to find out y for the three agents. Compare the agent with the maximum value of y wins. So that is the optimal y. So corresponding x is the optimal value of x for which y will be optimal. Now you can continue this up to 100, 1000, 10,000 iteration as you will. Okay, and you can also change the number of agents from 3 to 5, 5 to 10, any number of, no restriction is there. Clear? And each agent can be of n dimensional. That means it can be of 1D, it can be 2D, it can be 3D. That means if this each of x can hold more than one values, right? For example, if you are dealing with position, real position, spatial coordinates, then your x can hold x, y, z, lat, long and elevation, 3 dimension, right? So in this case, in this way, similarly, your agents can have 3D, 4D, 5D, any D of your choice, no restriction. But for simplicity, I have used 1D and only 3 agents, right? So the first step is to generate the population. Second step is exploration, where you compare your fitness value, that is the value of y, with the fitness value of the target agent or the prey agent. That means the agent within your considered agents that you have randomly selected as the agent who have already identified the prey, right? So the fitness value of that agent, with that you have to compare. If it outclasses the fitness value of the other agents, then you have to you know what you have to do. If the fitness value of the other agents is more than fitness value of the prey agent, use equation 1, and if your prey agent has outclassed your other agents, you have to use equation 2. It is as simple as that. And then the last step, exploitation. Again you generate x value for each of your agents. If it is 3x values need to be generated. If it is 5x value need to be generated. And after you generate it, you have, for that generation you have to use this formula, where the old x is the old x of your agents. R is 0.2, small t is the current iteration, big T is the maximum number of iteration that you have allowed. Rand is, all the rand are same, the random function. Okay, so what we are saying is that you have to use this exploitation phase, you have to use this equation, and where this x is at the old value of x of your agent, and rand is the random function, all the random functions are same. So again you generate 3 new value of x, from that 3 new value of y, compare with each other, the maximum wins, because you are dealing with the maximum optimization technique. Now how you can do this or execute this optimization technique in an Excel sheet? Let us see that. Okay, for this you see this x1, x2, x3 columns is our 3 agent. If you are considering 5 agents, you have to use 5 columns. If 10 agents, you have to use 10 columns, and so on. Now you see, from this, what I am doing here, I have used the formula for this initialization of the population, right? This formula is used here, lower bound plus random function multiplied by upper bound minus lower bound. As lower bound is minus 100, minus minus, it becomes plus. I think it is clear. For three separate formula I have to use. With the help of that, I have calculated the value of y. You see, b2 whole square, y b2 is the position of the cell, x1 is in b2, so this is b2 square, correct. Then it is c2, then it is d2. Now let us come into the exploration phase. So in case of Excel, I don't know whether which y will be greater than which y. I do not know that currently. So I have to use both this one, both equation 1 and equation 2 to generate the value of x and then to generate the value of y. Okay, because I do not know which y is better. The prey y is the better or our agent y is the better. I do not know. So that is why I have used both the equation to calculate the value of x for both the equations. So x e a1 means x small e is the exploration phase, indicates exploration phase. A is the equation 1 and 1 is indicates the first agent. Then you see next one, x e b1. So e small e exploration phase, b is the second equation and 1 indicates the first agent. Similarly for second agent I have used this, third agent I have used this. If there are 4, 5, 6 I would have used like that. Then at the time of calculating y I have used this check. You see this check, this one. And here I have randomly selected agent 1 to be the prey agent. So I am comparing with the prey agent only. So here you see, as I have said, prey agent is also an agent. So you have to do it for the prey agent also. The check, you have to do it for the prey agent also. So that is why I begin, y1 is the prey agent. So I begin with the prey agent. So if e2 is greater than e2, then first equation. If not, second equation. That means first equation value is stored here, so h2. Second equation value is stored here, so i2. Clear? Similarly j2, k2, l2, m2, and y1 is the y of agent 1, y2 is the agent 2, y3 is the agent 3, and these are all for exploration. Next come the value of x that I have calculated with the help of the exploitation equation. Now here also I do not know which value will be the old x, whether it will be the equation 1 value or it is the equation 2 value. So I have used generated x for both. So this capital E is the exploitation phase, A is for this A, the first equation, and 1 is the agent 1, and B is the second equation, 1 is the agent 1. Big E means exploitation phase. So similarly x for second agent for both A and B, and 3 is the third agent for both A and B. And then I have used the same check that was used in the exploration phase and I have found out that which x is actually utilized. So accordingly I have find this if that statement. If e2 is less than n2, then q2 square, otherwise r2 square. What is n2? N2 is this one. So the same thing I have done, but for the values generated with the help of the third equation. Okay. Now once I found out the value of y1, y2, y3, simple maximization function was used within this, and accordingly we have find the value of y for which value of the y which is maximum among the three agents. So I have identified that, and with the help of lookup function I have identified the value of x for which this y is maximum. So this is the simple thing, that is, just remember that in case of Excel you have to calculate both the equation whether or not your agent outclass the prey agent, right? And in case of exploitation phase also you have to calculate 2x for each agent with the help of the equation of exploitation, not with the help of the equation of that exploration. Okay, with the help of the equation of exploitation, you will calculate 2 times for each agent. Then when calculating y1, y2, y3, you just use the same check that you have used for in or during the exploration phase, and that will give you the what I will say, that will give you the value or the x that has been used in the exploration phase to generate the value of y. Okay, but here one thing you must remember, because in case of exploration phase you are comparing with the y's which are deducted from the random population initiated with the help of this one. But in case of exploitation phase, when you are checking, you will try to compare the y's that you have found from the exploration phase, because remember we are updating the position. So if already optimal y is selected or identified in the exploration phase, we cannot deny that, we cannot ignore that. So we have to compare with the exploration when we are comparing at the exploitation. That is why you see this check, if E2 is less than N2, you see N2 here. N2 is the y after exploration phase. Then O2. In case of Y2 exploitation, I have used O2. Then for Y3, I have used P2, not E, F and G. Just remember that, because it's a updation. We cannot ignore the optimal if already identified after the exploration phase. Remember, you are beginning with the initialization phase, then you are moving towards exploration phase, right? Then you are moving towards exploitation phase. All are updation. Okay? So you cannot ignore the updation done in the exploration phase. You have to consider that also. Okay? So that is all for this Pelican optimization technique. Try to practice it with your problems. If you find any confusion or problems, comment me. And if you like the tutorial, then subscribe to the channel and like and share it. Okay, so that is all I want from you, so that I get encouraged to prepare my next tutorial on bio-inspired optimization technique.